Okay, so continuing from the problem that we were doing. So we said that there's a uniform supersonic stream with Mach number 3, right? So it encounters a corner that deflects the stream by an angle theta equal to 20 degrees, right? And we calculated the shock wave angle, which is beta, then the parameter speed, pressure, temperature, Mach number, and stagnant conditions behind the shock wave, right? And so these are the conditions that we started with, right? So these were the conditions. Okay, and the corner was deflecting it by 20 degrees. Okay, now so this was what we did, and we calculated the parameters. Now let us do something over here. Now keeping all these parameters, this is the without changing m1, keeping p1 same, t1 same, just change theta to 30 degrees, right? So basically what we're talking about is that we have an oblique shock resulting, right? This is a free stream, right? And then this is something we had to calculate. This beta was something that we had to calculate, and so this streamline is getting deflected this way, and this was getting deflected by 20 degrees. So this is the theta. So now we are saying, and this is happening because of a corner like that, right? This is a physical corner like this, right? And this corner is resulting in causing this shock wave, right? And deflecting it by 20 degrees. Now we're saying that let's increase this this theta by 30 degrees, okay? And then keeping these parameters the same, let us calculate the pressure and the Mach number, right? The pressure and the Mach number on this side. So let's see what we will do in that case, okay? Okay, so for this here again, so for m1 equal to 3 and theta is equal to 30 degrees. So from the theta beta m relationship, from the theta beta m diagram, we get, so for this, we get a beta. This is from the from the theta beta m diagram. Okay, so from theta beta m diagram, we get beta is 52 degrees. Okay, so therefore again, right, so the normal component then comes out to be, right, so then again using the normal shock tables, right, from normal shock tables. So again what we get for normal shock tables for this Mach number, right? So for this Mach number we get and mn2 as, right. So from here we can calculate P2 and M2. So P2 therefore we can calculate as this into P1. P1 is known, so which is, right, and M2 again right? So that comes out to be 1.41. Okay. Now, what will be interesting is that we will kind of compare the three cases, and we'll do one more case from here and then see the difference. Okay. Then you'll probably understand what I'm trying to get at over here. Okay. So this is what we needed. So this is we calculated that. So again, so what we did was, keeping the input conditions the same, we increased the theta, right? And these are the values that we get. Now, what we're basically going to study now is what exactly is it doing to the shock, right? In the sense that, is the shock becoming stronger or weaker, or what exactly is happening? How do we find that out? Okay. All right. So let us do another case where we increase the Mach number. We increase the Mach number, and we keep that same, we keep that same, and keep theta also same to 20 degrees, right? So compared to the first case, so we just increase the Mach number and keep everything else same. The second case was, we kept everything same, just increase the theta. In this case, we keep everything same and increase the Mach number. And for this case, let us see what is happening. Okay, and the same and for this case too, we will find out the pressures and Mach numbers behind the shock. Okay, so here too we go about the same way again, right? So for Mach number, Mach 5, right? Mach 5, theta is equal to 20 degrees. Then from the theta beta M diagram, right, we get 30 degrees. Okay, so therefore again we calculate the normal component. We calculate the normal component to be 2.5, right? Then corresponding to this Mach number, we use the normal shock tables. Right? So from the normal shock tables, basically from the normal shock tables, what we get is right, and N2 to be 0.513. Okay, so therefore from here we can find out P2 to be right, and M2 to be 2.95. Okay, so pretty much if I were to sort of summarize this, so what we are given is, this is an oblique shock study, right? We're studying the properties across an oblique shock. So we are given the Mach number, we are given a corresponding deflection angle, right? So first things we do is recognizing that the flow properties across a shock wave are governed by the normal component of the input Mach number, right? So therefore from so this is not the Mach number which it will depend on. It will depend on the normal component of this, right? So therefore first things we do is go to the theta beta M diagram, right? This is again available in a standard book, and then we calculate the beta, which is the wave angle, right? This is the angle at which the shock wave is inclined to the horizontal. So then we get that angle, and then we calculate, based on that we calculate the normal component. Now this normal, once we get this normal component of the Mach number, we just go to the normal shock tables, which we've been using so far, and we calculate all these ratios. So there are other whole set of parameters. Right now we are using just the pressures and the Mach number. So these are all available. And what you should note is that this is the M2 in the tables, right? So for oblique shock though, in here it is the normal component of the M2. It is not exactly the M2. So, we need to calculate the M2 from there, okay. So, which we do over here. Okay. So, like we use the normal component of the Mach number to calculate these properties, the Mach number that we get here behind the shock is also the normal component, okay. And from there we calculate the Mach number. Okay. So, now what we will do is we will sort of list out the property changes for the 3 cases that we just did. Okay. So, let us do it here and see what inferences we can make. So, say this is M1. Okay. This is M1, this is Mn1, okay. So, let us list out what we got for the 3 cases. Now, the first case was Mach number was 3. So, we got these values. Theta was 20 degrees, beta came up to be okay. So, this was the first case for a Mach number 3, theta 20 and P1 to be 1. Okay. So, this was the first case. Now, the second case is again the Mach number is the same. Okay, sorry. This is 2.364. This is 1.41. The theta, we increase the theta. Okay, beta is 52 degrees, P1 is 1, and this is 6.276. Okay, and the third one was the Mach number is 5, then the normal component is 2.5, 2.95 actually. No, 2.5. What am I writing? Okay, and M2 is 2.95. Theta is same. Beta comes out to be 30 degrees. Okay, this is 7.125. Okay, so say let's just say that around 6.3, 7.1. Okay, I think that is it. Okay, so this is what. Now let us look at this chart a little intently. Okay, now just consider case 1 and case 2. Okay, now when we keep the Mach number same, all we change is the increase in the theta, increase in the deflection angle from 20 to 30 degrees. What happens? And the pressure input, the incoming pressure is also same, right? Now what happens is, what we see over here is that there is a large increase in the beta, right? There is a large increase in the beta, and this corresponds to a large increase in the pressure. So there is a large compression, right? And the Mach number actually decreases from 2.03 to 1.41. So this is, so what we can say is that if we increase the theta, there is a pressure increase, it causes a stronger shock. Okay, with increase in the deflection angle, there is a stronger shock with a corresponding increase in the wave angle, right? So if I were to write that down, if I were to kind of, say write that down, let's see. Okay, so increase in theta, right? Increase in theta results in a corresponding increase in beta, right? And causes a very large compression, because it goes, you can see this is what defines actually the pressure on the pressure behind the shock is what will define whether it is a stronger shock or a weaker shock, right? So when in this case what we see over here is that we have a large increase in the pressure, right? So this causes a larger compression, and this basically results in a strong shock, right? It results in a strong strong shock, or let's say stronger shock. Okay, so basically if from this condition I increase, for this condition I increase the theta, I will get a stronger shock compared to what we have over here. Okay, that's what we mean. Okay, then say between 1 and 3, okay, these are the two we compared. Now let us compare this and this, right? Now we keep the theta constant, and we increase the Mach number. Okay, what we see is that there is an increase in the Mach number behind the shock wave. So there is an increase in the Mach number from 203 to 2.95. There is actually a decrease in the beta. Now a smaller beta actually results in a smaller pressure, but here, although this is smaller, this is kind of compensated with the increase in M1 and the increase in M2, right? So which finally results in a large pressure, which results in a larger pressure behind the shock, which means we have an even larger, even stronger shock. Okay, because this change in pressure is smaller than this change in pressure. So for this particular case, if I keep the theta constant but increase the Mach number, I actually get a stronger shock even compared to this, right? So what we can say over here is that increase in Mach number right. So here, yeah, so for this case actually I think we should write that the Mach number is not changing for a given Mach number, and in this case the theta is not changing, right. So the increase in Mach number, you know, causes a decrease in the beta, right. It causes a, right, but this too causes a stronger shock. I think I should write stronger. Okay, so that's what we can see from here in this particular case, right? And also between these two cases, you can see that there is an increase in the Mach number, right? There is, however, a decrease in the theta, right? We still, and there is a corresponding decrease also in the beta, therefore, right? But we still get a stronger shock because the pressure still increases, so there is a larger compression in this particular case. Okay, so so basically what we try to do over here is try to get an idea as to how changing the you know, when we are using the theta beta m relationship, right? This is a relationship which is basically governing the nature of the shock. Is it a stronger shock, is it a weaker shock, or what it is, right? So that's what we try to show over here, that in how that these depend on each other, right? So this like a small example to show how we change the Mach number keeping the theta constant, or change the theta keeping the Mach number constant, and how the nature of the shock changes. So basically the nature of the shock, the strength of the shock is defined by this pressure behind the shock, right? So that you can see that for both these cases that pressure is increasing, so you actually get a stronger shock if you do these. Okay, all right. I think one of the more important things also when we study shocks is the interaction of shocks. Okay, interaction of shocks, and let us try and understand what that means, and let's kind of just do a problem and see if we can you know, get at what we're trying to do over here. Okay, so okay, let's look at this particular problem, say. Okay, so we have a horizontal supersonic flow, right, at a Mach number of 2.8, okay, and with a static pressure 1 atmospheres and temperature of 288 Kelvin. So this passes over a compression corner with a deflection angle of 16 degrees. So the same thing like we did in this case. There is a slight, we'll add a little more complexity to this. Okay, so essentially what we have is a compression corner like that, right, and this is 16 degrees, right, and we have a flow coming in, right. This Mach number is 2.8, okay, and the pressure is 1 atmospheres, and the temperature okay. So this passes over it. Now what happens over here is that there is a so basically an oblique shock results. Okay, so we have an oblique shock. Oh, now let us just for this. So basically this is my Mach number. Okay. Okay, so we have that, and then that deflects like that. Okay, so we have that. Okay, so this is essentially by 16 degrees. Now the oblique shock generated at the corner propagates into the flow. So this is the oblique shock, right? This is generated over here. Now it propagates sort of into the flow, and what happens here is that we actually have a horizontal wall over here. Okay, now this is a shock. This is a shock. It propagates like that, and it it hits this wall. Okay, okay. Now let me sort of do this artwork a little better. Okay, so say this is my 16 degrees. Okay, this is the 16 degrees. And okay, so this is it. Okay, now so this is something that we are familiar with so far. You know, this is something that we did just now, right? We calculated all the properties, etc. So we have a impinging flow. It hits an oblique shock, and the shock wave is happening because there is a sharp corner over here, a deflection, and that therefore the streamline then gets deflected because it encounters this shock wave over here. What we are doing here is adding one more complexity, is that this shock wave is now propagating, right? It developed over here, it's moving in here, and it is hitting this horizontal wall. Okay, the question is what will happen? The question is what will happen if this shock hits the wall over here? Okay, and in that, and then what happens to this deflection, this deflected streamline? Does it deflect furthermore, or it just remains like that? What happens? Okay, now that is what we need to study over here. So these are the properties which are given. Okay, okay. So now let us just sort of study this a little bit. So first question is what will happen if this is so? Okay. Now, first things first is that basically if you look at this streamline, right, this is the incoming streamline. So, if you have, so let us sort of call this region as say 1. Okay. Now, when it moves into say this region 2, let us call this as 2. Okay. Now, this streamline when it comes over here, right, now when it hits the wall, okay, now the boundary condition at the wall will require that this, okay, becomes parallel. This becomes parallel to this to the horizontal wall. That right now it is say at an angle. Let's call this angle as theta right now. Okay, so right now this is theta. Right, the angle that this deflected streamline is making with the horizontal is theta, right. But if this streamline were to hit here, hit this wall, the boundary condition says that it has to go parallel to the wall, right. So, if it has to do that, then this streamline has to deflect again, right, deflect again. And how will that deflect? It has to deflect downwards, right. So, it has to deflect that way, right, here this way. So, let us call that theta. So, in this case, so therefore, this is the theta, which is a deflection, right. So, this is the theta deflection. In case here it has to deflect like that, and then it becomes this, right. And how is this possible? How is this going to be possible? The boundary condition definitely imposes that this is going to be like this, you know. How is this going to be possible? This is going to be possible if this shock actually reflects from there, so we actually have another shock over here, so that this right, so that this streamline, when it encounters this shock, right, which is basically reflected from this horizontal wall, right, then it gets deflected by theta, it deflects itself by theta, and it becomes horizontal, right, it becomes horizontal. So, then therefore, so this shock, right, this is the incident shock. So, this is called the incident shock, and this is called the reflected shock. Okay. And in here what we are asked basically, so therefore, okay, so if we do this, so this is the theta, and if you look at this, so therefore, this is say a beta, right. And so what we are asked to find out here, okay, what we are asked to basically find out is the angle that this is making. So what we need to find out is this, right. So now this phi is basically the angle which the reflected shock is making with the horizontal, right. And this theta and beta is basically from our definition, right. So we have this normal shock, this is the incoming streamline. So we draw according to that, and based on that streamline, this is the deflection and this is the angle of the shock. Right. So in here for example, so this is yes, so in here this is my theta and this is my beta, right, for the incident shock. This is my beta. Okay. So therefore, let us just call this as 1 and this will cause us 2. Okay. And we can call, say essentially, yeah, we can say call this as section 3. So what we are asked to find over here is that we have a given condition. So these conditions are here. okay, right before the incident shock. So these are the conditions. So and the deflection angle is also given to be 16 degrees, right. So this theta is equal to 16 degrees, right. What we need to find out here is the angle phi. We need to find out this angle phi, okay, and okay, and the Mach number, pressure and temperature behind it. And the Mach number, pressure, so basically you can say this Mach number, are we calling this as M2? Let's see, what shall we call this? Yeah, we can call this M3 or whatever it is. So basically this M and the pressure and temperature, right, behind the reflected shock. So this is what we have. So how do we go about here? Okay. Now the only thing what you can see over here is basically that in it, so far what we've done is, if you just sort of erase this part of the picture, we are familiar with how we are going to tackle if we have an oblique shock, right. So then we had the input Mach number, we have a theta, so we can calculate the beta, and then we use the normal shock tables. That's something we've just now done. The added complexity here is now that we've explained what's going on, forget about the wall. What we have is, once this gets deflected, it is again hitting another shock wave. Okay? So in this case, this is a reflected shock wave, never mind where it comes from. Numerically, what it comes down to is, once we calculated these values for the incident shock like this, it again hits another one. Okay? And then again, we just need to calculate the properties across this. Okay? So that's all it comes down to in terms of numerics. So let us see how we will use, we just need to be a little familiar or just careful as to these angles and definitions and so on and so forth, right. So let us see what we will how we'll go about calculating the properties in this case. Okay. All right. Okay, before we do that, let me just emphasize one more time. So now this is the compression corner, right? So this is the angle of this is given, which is 16 degrees, right? So what we're saying is that if you have an incumbent streamline like that, that gets deflected by 16, right? Now this theta and this theta are same, yes, because now when this is hitting the horizontal wall at 16 degrees, the boundary condition forces it to become parallel to itself, which is this. So therefore this becomes theta. The only difference I hope you can see is that in here it is deflected this way, in here it is deflected this way. So basically their senses are different. Okay, if you consider this to be positive, then these angles can be negative. Okay, but the theta here though is the same. The value of that is same. Okay, having said that, so let's again. So for let us look at this part for the incident shock. Okay, now for the incident shock, okay, so now we have an M1 as 2.8, right? This is 2.8. We have a theta 1 to be 16 degrees, right? Then, like we've done before, we use the theta beta M diagram, right? We use that, and what we get is the, okay, so there we go. One little calculation, and we are able to calculate the inclination of the incident shock with the horizontal, right? So now we know that this is 35 degrees. Okay, what now we need to calculate? So our main aim basically is to calculate these properties. Okay, so what do we do now? What do you think we should do now? Okay, now what we should get here basically, if I had to, like for this particular this particular shock, the incident shock, we needed this Mach number, right, and we needed the inclination. Now, in this case, what do we need to calculate these properties? We also need the incoming Mach number. So, that incoming Mach number is this. So, say let me call this as M1, okay. This is 2.8 and this is M2. This is the M2 we need, so that finally we can calculate, say that M3, that region is 3, right. So, now this M2, how do we calculate in case of the incident shock wave? Now, what we will get from the tables is the normal component of this M2, right. Since we know beta, since we know theta, then we can calculate M2, right. So, that is the reason the first things we need to calculate is this M2. Okay. So, if we do that, so using this, so what we will calculate is the normal component of the incumbent Mach number for the incident shock, and that is, okay, I will sort of write this. Okay. This is something we have been doing, right. It is this. Okay. Now, corresponding to this Mach number, corresponding to this Mn1 equal to this from the normal shock tables. Now, from the normal shock tables for this Mn1, what we get is okay. And so again what we get is the normal component of M2, right. So, then from here we can calculate M2, right. Now, we can calculate M2. Right, that which is equal to 2.053. So, basically this Mach number here, so therefore, this Mach number out here so this Mach number is equal to, right. So, it comes from 2.8 and reduces to 2.053. So, this is my Mach number here. All I need to do now is using this Mach number and this reflected shock calculate these properties. Okay. Now, since the geometry is slightly different from this, let us see what we will do. Okay. What these values exactly mean to us. Okay. So, in here, so therefore, okay, did we calculate beta 2? Okay, right. So, therefore, we have this, right. Now, let us do it for the reflected shock. Okay. So, we have, say, so this is between regions 2 and 3. Right. So, in the for the incident shock we said 1 and 2, right. So, 1 and 2 we calculated M2. In this case we will go from 2 to 3. Okay, that is how I am denoting it. So, we know M2, just note that in this case the impinging Mach number is M2. Okay. So, M2 in here is 2.053. Okay. Beta 2 actually, okay, yeah. Theta 2 is 16 degrees. Okay. Now, if I do this, so what do we have over here? So, in this case, we have this Mach number, okay, this Mach number which is getting deflected by theta, right, and that theta is 16 degrees. Okay. Therefore, we can now calculate the value of basically beta 3. right. So, for this, and this we use the, so from the theta beta m diagram, so beta 3 we get as right 45.5 degrees. Okay. So, this is the okay, actually I write this as beta 2. Okay, no problem. So, let us write that as beta 2. Okay, let us write that as beta 2. So, now this is basically the wave angle for the reflected shock, right, and this we get from the theta beta m diagram. Okay. So, we know the incoming Mach number, the theta, the deflection angle is 16 degrees, we get a corresponding beta 2, right, which is 45.5. The only thing is, in this case you can see that the definition of beta 2 is this way. Okay, this is the angle which it is making with beta 2. What we have to finally find out is the angle of this shock with the horizontal. I hope you can see what we are exactly doing there, right. So, we will find that out. So, this beta 2 essentially is that from the incident streamline, the angle it makes. So, beta 2 is basically the angle between the incident streamline and the reflected shock, right. So, this is the definition. So, this is the beta 2 that we get. Okay. So, now we will basically proceed the same way. Then the corresponding normal component of the incident Mach number will be again right. So, this is 1.46, right, and then corresponding to this what from the normal shock tables, what we can find out is the P3 by P2, which is 2.32, T3 by T2 is 1.294, and Mn3, right, Mn3 is this, right. Okay, having got this, now let us see how we will calculate the properties right behind the reflected shock. Okay. All right. Okay. So, having got this, this is what we get. So, let us first calculate the M3 actually. Okay. Now, let us calculate the M3. So, M3 is equal to Mn3 by sine beta 2 minus theta 2. So, this theta 2 is actually just the same. So, here what we get is M3 is basically 1.45. Okay. So, now let us calculate the properties. So, what we need to get is P3, right. So, P3 will now just basically play around with the ratios that we have got. So, we got a P3 by P2, we earlier got a P2 by P1 into P1, right, and this comes up to be P3 is 6.54. Okay. Okay, you get this. So, P3 by P2 is what we get over here. This is the ratios I've got. I also got P2 by P1. Okay. Now, if it was required to find out pressures and temperatures in this region, that also we could have done. Okay, we could have done that from here as well, because we know P1 and T1, but it wasn't required. What we needed to just know is the properties in this region. Okay. So, for that we are going to just play around with these ratios that we calculated and just get that. So, similarly T3 will be T2 by T1 into T1, and that comes up to be okay. Okay. So, this is what we get. Okay. So, essentially what we have been able to do is calculate the properties in this region, right. Now, let us see if we can find out what phi is. Okay. Let us see if we can find out what is phi. Okay. So, what exactly is, how do we calculate? This is beta. So basically this is the angle, the phi is the angle with the horizontal. Okay, so if you look at this, just this picture over here, this is the beta 2, right? So what I need is this angle. So what I need is this angle, right? This angle is what I need. This is my phi. So this is beta 2, this is beta 2 minus theta. Isn't that obvious from in this diagram over here? So this is the beta 2, and what I need is this. This part of the angle is available. So essentially, therefore, I can write that phi is equal to beta 2 minus theta, right? And that comes up to be that, okay, around 30 degrees. So what you see over here is that therefore in here, this is a reflected shock. So the reflected shock, actually, what is beta 1? Beta 1 is 35 degrees. Okay, so the beta 1 is actually, say if you look at this, it is making 35 degrees. So it, at an angle of 35 degrees, the incident shock hits the horizontal wall, right? And from there it again deflects downwards. It gets reflected from here, and in the opposite direction, right? In the opposite direction, it makes around 30 degrees, right? So therefore, if I have a streamline, if I have a flow coming in here, it gets deflected by the incident shock, as well as this shock will interact with the reflected shock over here and get deflected further, right? So let me just sort of write down the properties here, just to kind of draw a little bit of conclusion, and let's see what exactly is happening over here. Okay, so okay, this is becoming a little congested, so let me just write it this way. Okay, all right, so this is it. Okay, so what we have is, these are the properties. Okay, so these are the properties right, and T is 288 Kelvin. Okay, so this is what we get. Ouch. So let's erase all of that. Okay. Okay, so here this shock makes an angle 35 degrees, okay, and this deflection is 16 degrees, okay. So therefore, now this is M1, and if I were to call this as M2, right? Now this M2 is equal to, M2 is equal to, right? Now we could have calculated P2 and T2 over here, actually, okay? So, well, we could have actually done that, just because P2 is 2.82 atmospheres, because P1 is 1, T2 is 1.38 into this. We've got the ratios over here. Okay, so and then it hits the wall over here, and this is what it is. So therefore, okay, now this, so then this becomes M3, right? And that M3 is equal to what? 1.45. Okay, so goes from 2.8 to 1.45, right? So then this gets deflected by 16 degrees, okay, and the angle that the reflected shock is making with the horizontal is around 30 degrees. Okay, and the pressure here P3 is okay, so I didn't write that. Okay, 6.54 atm. Okay, so this is region 3, right? So P3 here is 6.54 atm, and temperature is 517.8 Kelvin. Okay, so what essentially we can see over here in the previous example, for example, we were having a Mach number of say 3, and we reached a pressure, we just passed it across an oblique shock, and we got a pressure around somewhere around 6.5, etc. Okay, just go and look at that example, just the previous example. But here we actually have a smaller Mach number, we have a lesser Mach number, we kind of get the similar kind of a pressure change, similar kind of a compression, okay, with a completely different sort of shock setup. Okay, so we have an incident shock and a reflected shock, and it goes through these 3 regions, it deflects twice, and this is the kind of pressure changes and temperature changes that we are looking at. So I think it's a good idea to go and look at the previous example and compare that with the pressure changes and temperature changes in this example, right? Okay, so that should be all. What we will kind of try to do this is the P theta diagrams, and kind of do one more problem on this to kind of get a feel for how shocks will interact and so on. Okay, thank you. That should be all.